You ever take a photo that you thought was going to be perfect, but then you look at it on your screen and it's just a blurry, badly lit mess? Yeah, we've all been there. For us, it's just annoying, but, for a self-driving car or a medical scanner, that kind of mistake can be a critical failure. So today, we're going to pull back the curtain on how computers learn to see clearly, fixing all those little imperfections in our visual world to actually make sense of it all.
So, first question, and it sounds totally backward, right? I mean, our world is bursting with color, so why on earth would a computer's first move be to just throw all that amazing information away? Well, it's because sometimes, to see what really truly matters, you have to get rid of all the noise first.
Okay, take a look at this winter scene. On the left, yeah, the colors are beautiful to our eyes. But for a computer that's just trying to figure out where's the bridge or what's a tree, it's a ton of confusing data. But now, look at the right. The moment you convert it to stark black and white, the core structure just pops. The lines, the shapes, the edges, they're all suddenly crystal clear. It gives the algorithm a much simpler map to work with. Now, this whole process, this act of making that black or white decision for every single tiny pixel, well, it has a technical name. It's called binarization. Let's dig into how it actually works. So, binarization, or as it's often called, thresholding, is built on a really simple idea. Every pixel in a grayscale image has a brightness value, right? It goes from 0, which is pure black, all the way up to 255, pure white. Thresholding just draws a line in the sand. It sets a threshold value, and then it forces every pixel to make a choice. Are you on the lighter side of this line or the darker side? And here's how that plays out, broken down into 4 simple steps. First, you just pick a threshold value. We'll call it T. A lot of times people start with 127 because it's right in the middle. Then, the computer just zips through, 1 pixel at a time. It checks. Is your brightness value bigger than T? Bam, you're white now. Is it less than or equal to T? Okay, you're black. That's it. It's a really elegant, simple, and super fast way to simplify an image. But, and there's always a but, right? That simple one-size-fits-all approach, using just one threshold for the entire picture, it's got a massive flaw. What happens when the lighting in your picture isn't perfectly even? And this right here is exactly where that simple method just completely falls apart. This is a photo of a poem. It was taken in pretty bad light, and you can see there's a shadow, making the bottom of the page way darker than the top. For a single global threshold that's supposed to work for the whole image, well, this is an absolute nightmare scenario. And yeah, here's the disaster. The computer used one threshold, just one number for the whole picture. Up at the top where it was bright, it kind of worked okay. But down at the bottom, in the shadows, almost every single pixel was darker than the threshold, so the computer just turned it all to black. The text is gone, it's completely lost. So clearly we need a smarter way to do this. And lucky for us, smarter methods exist. So let's look at a couple of the more advanced techniques that can totally solve the problem we just saw. We're talking about adaptive thresholding and a really brilliant approach called Otsu's method. So what's the big difference? It really just comes down to one word: flexibility. A global threshold is rigid. It's one rule for the whole image, period. But adaptive thresholding, it's smart. Instead of one rule, it looks at a small neighborhood of pixels at a time and calculates a unique custom threshold just for that tiny area. It literally adapts to the lighting conditions, section by section. And there are a couple of main flavors of this. Adaptive mean just takes a simple average of the pixels in that little neighborhood to set its threshold. Adaptive Gaussian is a little more sophisticated. It calculates a weighted average. It says, hey, the pixels closer to the very center of this neighborhood are probably more important, so it gives them more influence. Either way, both are a huge leap forward. But what if you didn't even have to guess at the settings? What if there was a method that could just look at an image and find the single, mathematically perfect dividing line between the stuff you care about and the background, all on its own? Okay, now, don't let this formula scare you. The idea behind Otsu's method is pure genius. Instead of us trying to guess a threshold, it looks at a histogram of all the pixel brightness levels in the whole image. And then it automatically finds the perfect dividing line. Its whole goal is to create 2 groups of pixels, a black group and a white group, where the pixels inside each group are as similar to each other as possible. It mathematically finds the most natural split. It's incredible. And the results, they can be absolutely stunning. On the left, you've got this murky, really low-contrast sonar image of a shipwreck. It's almost impossible to see any detail. But on the right, after applying Otsu's method, wow, the result is just crystal clear. The ship's structure is perfectly pulled out from that noisy background. It's just an incredibly powerful and completely automatic technique.
Okay, so now we know how to isolate an image's core structure, but what if that structure itself is full of errors? I mean, binarization isn't going to fix an image that's already corrupted from the start, and that's where our second topic comes in, clearing up the digital static that we call image noise.
So what exactly is noise? Well, at its core, it's just random garbage in your image that wasn't actually there in the original scene. Think of it like the static you hear on a radio when you're between stations. It's just interference that's getting in the way of the signal you actually want to hear. In an image, that interference shows up as random changes in the color and brightness of the pixels.
And here is a really stark example. The MRI scan on the left, it's clean. The one on the right is absolutely corrupted with noise. You can see right away how that visual distortion could easily stop a doctor or a diagnostic algorithm from spotting something critical. When it comes to an image like this, the stakes are unbelievably high.
And this noise, it isn't some digital ghost. It actually comes from real-world physical stuff. You know, trying to take a picture when there's not enough light, the heat coming off your camera's own sensor, a speck of dust on the lens, or even just errors that happen when an image gets sent over a network. All of these can add these ugly, unwanted artifacts.
Now, this is probably the single most important thing to remember about dealing with noise. There is no one-size-fits-all fix. You have to match the solution to the specific problem. It's just like how a doctor has to diagnose an illness before they can prescribe the right medicine. A computer has to first figure out what kind of noise it's looking at before it can apply the right filter to clean it up.
So, for our last little bit here, let's put on our digital detective hats and learn how to spot a few of the most common culprits behind all this digital mess.
All right, this table breaks down 3 of the big ones. First up, you've got Gaussian noise. This is that even, staticky grain you see a lot. It works by adding a small random value to each pixel. Then there's impulse noise, which people often call salt and pepper noise. It does what it says. It just replaces random pixels with pure black dots or pure white dots. And finally, you have speckle noise. This one is more granular, and instead of adding to a pixel's value, it multiplies it by a random number, which can make already bright spots look even brighter and noisier.
So why does any of this matter? What's the big takeaway? It's that thresholding and noise reduction, these aren't just some abstract exercises for computer science class. They are the absolute fundamental first steps that allow all this incredible technology, from the computer vision in your phone to medical scanners that save lives to self-driving cars, to make sense of the visual world. Without these basic corrections, all of that amazing tech would be effectively blind.
Which really brings us to our final thought for the day. That image of the sonnet, the one that failed so badly, it's a really powerful reminder of the challenge we're facing. If a computer can be so easily fooled by something as simple as a shadow, what does that really tell us about the long road ahead, the journey to create machines that can genuinely perceive and truly understand our complex, messy, and beautifully imperfect world?